Today I would like to go over finding the convergence and divergence of geometric series. So by series, we mean we're adding numbers together. We're adding terms, geometric sequences in particular together. And let's say we have a geometric sequence like this. 2, and then a 1, and then a 1/2, and then a 1/4, then a 1/8, all the way down. And this is a geometric sequence, but let's look at the series. The series, we're just adding the numbers together. If you add all the numbers together, is there a point where you will actually reach, where you'll actually reach a number and not get any bigger? Now, you would think that it can't be that there's a limit for this one, because if you keep adding numbers, it's going to get bigger, right? But actually, it turns out that there is a limit for this sum. So to look at that visually, if you think of if you think of a wood that is 4 meters long. Okay, this is 4 meters long. And if you cut this wood in half, then this side is going to be 2 meters. This side is going to be 2 meters. And again, let's cut the second half in half again. So now we have 1 meter and 1 meter. And let's cut this one in halves again. Let's just cut the second one here. Okay, so now that would be 1/2 and 1/2. And if you cut that in half, it's going to be 1/4 and 1/4. Let's cut the second one here, okay? So that's 1/4 and 1/4. And if you cut this one, it's going to be 1/8. If you cut that one, it's going to be 1/16. And if you keep cutting it this way, this picture actually represents this series, because we have a 2 here, we have a 2 here, we're adding a 1, remember this was 1 meters, we're adding a 1, we're adding a 1/2, right? We're adding a 1/2, we're adding a 1/4, we're adding a 1/8, I'm running out of colors here, but you get the picture, right? So this picture actually represents adding numbers infinitely. And if you see, we're adding infinitely many numbers, but we're also making those numbers infinitely smaller. So we reach a point. What was the length of this whole wood here? The whole wood was 4 meters, right? So if you keep adding numbers this way, you're eventually going to reach 4. Okay, so mathematicians found that even if you are adding infinitely many numbers, you can still reach a certain number and not get any bigger than that. And this picture is a great way to see that, see why that is true. So this is called the converging geometric series. Remember from geometric sequences that converging means it reaches a certain value. Converges, it reaches a certain value, and diverges means it just keeps getting bigger, or it keeps getting smaller, or it just alternates indefinitely. It doesn't reach a certain value. Okay, and let me explain this. With a graph. So let's say we have a graph. A geometric series would look something like this. A converging geometric series would look something like this. It would go up, and it would keep going up, but it won't go past a certain value. It converges to this value here. It never goes, it keeps going up this way, but it never actually crosses that line. This is an example of a converging series. And obviously so the converging series, I'll draw it in blue here. That'll be converging. A diverging series could either go just get bigger infinitely like that. It can get smaller infinitely, or again, it can just go like that. It doesn't reach a certain value, okay? And even if it goes like this, if it has a linear increase, that's also diverging because it just keeps going up. It doesn't reach a certain value. It just keeps going up like that. So now this gives rise to the question, how do we know if a geometric series converges or diverges? And if it does converge, to which value will it converge? Okay, so the rule for convergence and divergence for geometric series is very similar to the rule for convergence and divergence of geometric sequences. So remember, for sequences here, I'll put a reminder up here. If the absolute value of r, where r is the common ratio, if the absolute value of r was greater than 1, then it diverged. Which makes sense because if it's greater than 1, you're multiplying a number bigger than 1 each time, and it's going to get bigger and bigger. If the absolute value of r was less than 1, it converged. The value of the number became smaller and smaller. And it's very similar for geometric series. If the absolute value of r is greater than or equal to 1, then it diverges. If the absolute value of r is less than 1, then it converges. So the only difference is that it has this little equal to sign for the series. Okay, and the reason is this. Let's say we have a geometric series where the common ratio is 1. So if we start with 1, we multiply by 1, the next term is going to be 1, next term is going to be 1, next term is also going to be 1, and it's just going to be 1 each time. If this is a sequence, this as a sequence doesn't diverge, right? It just keeps on repeating itself as 1. But this as a series, if you keep adding 1 to a value, it's just going to keep getting bigger and bigger, right? So that's why if it equals 1, if the common ratio equals 1, it's going to diverge because you're just adding the same number over and over again. Okay, and another thing that we can know, if it converges, we can actually know to which value it will converge. Okay, so let's look at, remember the formula for finding the first n terms of a geometric series. That equals the first term times 1 minus r to the power of n divided by 1 minus r. That was our formula. And if r, the absolute value of r is less than 1, so if r is less than 1, and if n gets bigger and bigger, then this value here, it's going to get smaller and smaller and smaller, right? It's going to be a fraction multiplied to itself, and it's going to keep getting smaller and smaller and smaller and smaller. So this will eventually become 0 as n approaches infinity. So this is for infinite series. If n approaches infinity, and if r, absolute value of r is less than 1, then this is going to become the r to the n is going to become 0, and our formula will simplify to this. So if we know that the series converges, then not only do we know that it converges, but we can also know that it converges to this value. It converges to this value, where A1 is the first term and R is the common ratio. So let's see if we can find some value of some of the geometric series. So let's say we have a series like this: 1, 1/3, 1/9, 1/27. Oh, it's the series, so we need to add these together. And let's say we want to find out what will this equal to. When n becomes really, really, really large, what will this equal to? And first of all, we need to know, will this equal some number? Meaning, will it converge or will it diverge? Oop, I forgot to put a E at the end of G here. Converges. Okay, so let's see if it converges or diverges. What is R? Just divides the first term, or not the first term, any term with its previous term. 1/3 divided by 1, so R is 1/3. And the absolute value of 1/3 is less than 1. So we know that it converges. Okay, we know that it converges, meaning that if we add all of them together, we'll get some number. And to what value will it converge? Well, it's going to equal this number right there. So that is A1 is the first term divided by 1 minus 1/3. So that is going to equal 1 over 2/3, which equals 3 over 2. So if you add up all the numbers like this, you'll eventually get 3/2. Okay, so that's how you add up infinite series. You can only add up infinite series if it converges. So let's see what happens if it diverges. If it diverges, so this sequence here is 5, 25, 125, etc. R is equal to 5 here, so that means the absolute value of R is greater than or equal to 1, which means it's going to diverge. And if we, as soon as we find out that it diverges, we can say that you can't add these together. Oh, I keep putting commas here. These should also be plus signs since it's a series. As soon as we know that it diverges, we can know that that is going to have no finite answer. Okay, because by the definition of diverging, it means it just keeps getting bigger and bigger and bigger. So this series doesn't have a finite sum. Okay, so the only time when a geometric series has a finite sum is if it converges. And if it converges, you can also find that sum by using this formula.